Hey, so it's back with another day. It's integration by substitution. It's our second day working with integration by substitution. So today's going to be a little more formal than what we've been working with, what you worked with yesterday. The last time we did, the sort of the hokey pokey method, but when I actually get into the math definition. So what we've got is we're taking the integral, the antiderivative of some function that's a composite function, so it's the f of the g of x. And within that integrand, the thing that we're taking the integral of, we've also got the derivative of that inner function. Okay? So what we do is we rewrite all this in various forms. So first we pick out the inner function. Okay, right here, g of x. That's kind of the thing, the inner function, and we call that u. Okay. We take the derivative of u with respect to x, and that's g primed of x. We write that in differential form, and so we get du equals g primed of x dx. So what that allows me to do is I can now substitute, instead of writing g of x, I write u. Instead of writing g primed x dx, I write du. And so I've got a sort of simplified function. It's the f of u du, which doesn't really sound nice, but we just work with it. It's the math notation. And that allows us to integrate. We'll show you what I mean as we work through an example, but it looks a little more formal. It's not meant to be all that much more complicated, but we'll see what happens, okay? So in this case, we're going to say u is my inside function because I've got something raised to the half power. So this is a function. This would be my inner function, my outer function. So u is equal to 3x plus 4. Right? Du is the derivative of 3x plus 4, which is 3 dx. So knowing what we know, to make this all work out, just missing the dx here, I've got to put a 3 in. I've got to take a 3 out. So when I do that, the 1/3 becomes the 1/3. Instead of 3 dx, which my integral sign is going to be there, instead of 3 dx, I'm going to write du. That replaces the 3 and the dx. And instead of 3x plus 4, I'm going to write u. So I've got u to the 1/2. So now I can integrate that because it's just a straight, power function, one of the patterns that we know about. The 1/3 is going to come along for the ride. It's going to become u to the 3/2 over 3/2, which I know enough to write as divided by, or instead of dividing by 3/2, I'll multiply by 2/3. Pop the c in there as soon as I get the opportunity. And now let's make it look nice. Let's see, 1/3 times 2/3 is 2/9. We back substitute in what u is. U is 3x plus 4 to the 3/2 plus c, and we're done. Okay. Could we have done this the hokey pokey way and just kind of gone with it? Yeah, we could have in this case. So, knowing pop the 3 in, take the 3 out, will work for us. But there's going to be situations, perhaps on the next slide, where you can't do that. So you have to be able to slow down, get yourself wrapped around what's u, what's du, do the full substitution, and make it all work. And if you're not really clear on the hokey pokey, slowing down this way sometimes makes it more clear what's going on and why we're able to do that. Okay? We're just trying to get our integral to look like one of the patterns, and away we go. All right. So in a case like this one, for instance, turns out to be one of the more difficult problems that we'll encounter throughout the rest of the semester, and it'll take a little while before we're good at doing it. So we'll do a little substitution. U is equal to 2x minus 1. Okay, because that's the thing that's to a power. Okay? Excuse me. Well, I'm not putting dx in here, but I should. Okay? Du is going to be the derivative of that, which is going to be 2 dx. Okay, so I just have regular old dx, so I'm going to put a 2 in, and as habit has it, put it in the front, 2 in, take the 2 out. So I've just effectively multiplied by 1, no big deal. So I want the ability to use different color ink, so all right. So 2 dx. Boom, 2 dx. Taken care of. 2x minus 1. Green. 2x minus 1. 2x minus 1. Taken care of. The only thing I don't have a cure for, I don't have a replacement for, I don't have something to substitute in for, is that x. I don't know what to do. I can replace 2 dx with the u. I can replace 2x minus 1 with u, but I got to do something with this x. Okay? So here's what I can do. If I know that u is equal to 2x minus 1, I can say that x is equal to u plus 1 over 2. Stop, pause, slow down, make sure that that makes sense to you. So now I can substitute this. I got it. So I got to go through and I've got to do this rewrite. And let's go back to black ink so that it's all good and nice. All right. So the half is part of the mix, coming along for the ride. Okay. Instead of x, I'm going to write u plus 1 over 2. Instead of 2x minus 1, I'm going to write u to the 1/2 power. Okay, just replace the green for the green. And instead of the 2 and the dx, I'm going to write du. Now right away you might be looking at that and going, well, gee, that was helpful, Mr. Take. That was really doesn't look any nicer than what it was. But here's what we're able to do now. This 2 is just as constant. So I'm going to bring that out in the front. So I've got that times u plus 1 times u to the 1/2 du. Okay? Now, before I couldn't distribute the x in there because of the exponent, but now I got my exponent outside, so I can distribute this in. So this becomes 1/4 integral multiplied through u to the 3/2 plus u to the 1/2 du. Okay? And from here, that's a jolly hand clapper. We all know how to integrate that. That becomes 1/4. Let's do a little brackety thing. U to the 5/2 divided by 5/2, which we're going to write as multiplied by 2/5, plus u to the 1/2. Oops, sorry. U to the 3/2. Let's fix that because that looks awful. 31/2. We'll be going. You said 31/2. U to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. Get that constant in there as soon as we possibly can, and then we just got to do a little bit of math massaging to make this all look nice. So when I distribute the 1/4 through, I'm going to have 2/20ths or 1/10, and back substitute what u is. U is 2x minus 1 to the 5/2 plus 1/4 times 2/3, 2/12, which is 1/6. 2x minus 1 to the 3/2, and don't forget c. And technically speaking, I've multiplied the c by 1/4. Okay, so I really should call this my first constant and this my official constant. This 4th times a constant is still a constant. And so that is the integral of this. And these take a little while to get used to. There's a lot of work. You can't do any kind of thing other than just writing a bunch of things down. Write down what u is, write down what du is, figure out what that makes x, work through, substitute, solve. Eventually, half dozen more times we'll get there. Okay? All right, so let's try this one. Remember, trickily enough, this is like that, right? You can rewrite that way. So this is the big u function. Okay, so we write this as sine of 3x. Derivative of sine 3x is 3 cosine 3x. So I'm pretty much got this covered, got that part covered. The only thing I'm missing is a 3. 3 in, 3 out. Rewrite 1/3 of the integral of u squared du. Okay? Sine 3x is u squared. All this cosine 3, this 3 cosine 3x dx, that's du. That's what all that stuff is. And so again, this is a nice one to integrate because we know how to integrate something squared. It becomes something cubed over 3. That's really helpful. I don't know why I can't do that. Plus c, so this is going to become 1/9 of sine cubed 3x plus c, and all is right with the world. Okay? So again, could you have hokey pokey that? Sure, probably. But slow down, write some things down, make sure it makes sense. If you can just look at it and get from there to here with just doing the quick step, then go for it. But if you're confused or you're not getting them correct, it's a good time to slow down. Slow down. Let's try this one. It might be the last one for the day. So the question is, like which one do you want u to be? Because they both look sort of conspicuously alike. But if you're looking ahead, you can go, oh look, this is the derivative of this. So let's make u equal to x squared plus x, and then du is going to be 2x plus 1 dx. Okay, when we rewrite that, we didn't need to do any other things to it. We just rewrite this as the integral of u du, and the integral of u du is u squared over 2 plus c, and so we back substitute in, we get 1/2 of x squared plus x squared plus c. Okay, could we have multiplied those through and done the thing? We could have. Sometimes this is a whole lot faster. It's a fine answer. We're there. Okay? Oh, I lied. Sorry. I misspoke. I did not lie. I forgot. There's one more to do. Okay? So there is somewhat of an advantage when we're doing a definite integral to doing the substitution method. Okay, I'll show you why. So we go x squared, u is equal to x squared plus 1. And du is 2x dx. Pop a 2 in, take a 2 out. Okay, can't just multiply them by. Let's do my substitution. Take 1/2 integral. I'll leave the limits alone for right now. Of u cubed du. Okay, so if I'm changing to u, I'm going to change everything to u. So my limits, instead of being 0 and 1, which are based on x, are now going to be, plug 0 in, 0 squared, 0 plus 1 is 1. So my lower limit is going to become 1. Okay, my upper limit, plug 1 in, 1 squared, 1 plus 1 is 2. So now, instead of integrating from 0 to 1, I'm going to integrate from 1 to 2 because I'm in terms of u. And what this will say means I won't have to do the back substitution step anymore. So this becomes u to the 4th over 4, and I'm going to evaluate it at 2 and 1. Okay, so this is what, 1/8 of 2 to the 4th minus 1 to the 4th. 2 to the 4th is 2, 4, 8, 16. Minus 1. Oops, don't forget the times 1/8. So this becomes 15/8. So the advantage, in this case of doing the substitution, is I didn't have to go back through. I didn't have to do that extra little piece. I just changed everything over to the u's, and it all worked out. It all worked out fine. Okay. Sometimes you see multiple choice questions where they'll say which one's equivalent to this, and if you just left these as 0 and 1s, that's going to be one of the choices, but the correct is that sort of thing. Okay, so substitution. It's about the same thing that we've been doing for a while, and there's a little bit more apparently. Jeez, it's almost as if I've forgotten that I made this. So we've got two different things, even and odd functions. An even function is symmetric about the y-axis. This sometimes will save you some time. So if you're integrating an even function from a negative value to the same, to its opposite value of the function, you can just do twice the integral from 0 to a because we've got that symmetry. The advantage there is a lot of times it's easier, particularly with a polynomial thing, to evaluate the function at 0 than it would be at a negative value. So if you recognize that you've got that symmetry, you can go, oh, hey, that's the same as twice from 0 to a. Okay. If we've got an odd function, which means it's symmetric about the origin, if we're going to integrate from a negative value to its opposite positive value, we're going to get 0. Because the negative part, neutralize that positive part, and it's going to work out to be 0. So sometimes that'll save you the time if you just can recognize, go, oh yeah, that's an odd or an even function. It just saves you from doing the work and coming up with 0. Okay? I think, really, I swear this, when I hit the next slide, it's going to be something else. It is. Okay, it's that. And those are that. And then we'll go back to that. Okay, so substitution. Same sort of thing we've been doing. Gets a little more difficult as we go. I think you're good. We struggle with it. We work with it. It's a little more difficult, but we're halfway through the calculus course, so sometimes things are going to be a little more difficult. All right, so if you have questions, you should ask. Thanks for watching. See you tomorrow.